Okay, I think it's time to start. Good morning, everyone. And today we'll talk about an important class of models, in particular AutoEncoders, and how they can be treated from the Bayesian point of view. So we will talk about variation AutoEncoders. They were quite popular some time ago, and they still can provide good performance with some problems. For sure, all of you know that right now the state of the art for generative models are something like diffusion models. And for diffusion models, maybe we'll give a lecture closer to the end of the course. And generative adversarial networks, kind of common and similar approach to think about how we can generate realistic data. But still, variation AutoEncoders remains interesting and probability-inspired approach. So I think it would be a good idea to talk about them during the course on Bayesian and probabilistic models in machine learning and deep learning. And it will be another chance to see how can we treat more complex models with our probabilistic framework. And so let's see how it looks. So we start very far away from AutoEncoders and variational encoders. We'll start with actually some kind of introduction into unsupervised learning. Then we go to AutoEncoders and go to variational AutoEncoders, and so it will be each by the end of the lecture. So as I hope all of you know, supervised learning, we see that our data consists of pairs of x and y's, where x is some future vector and y is some label. And so our goal is quite explicit. We want to learn the mapping from x to y. And so, okay, I hope we are recording here. Yeah, we are recording.
It is.
Okay, very good. And so we learn to imitate this mapping, and we have like quite large in case of image recognition data sets, maybe small data sets, but at least we have this explicit goal we define, we incorporate into our loss function. And so we can reformulate in this paradigm a lot of problems like classification, regression, even object detection, segmentation, and so on. And so, like, it's quite good and quite often it works very good. Okay. So a lot of pairs with some source image and some target. A target can be an image too, but for example, in case of segmentation, we can say that this mask you obtain is also an image, and this is what we want as an output. For supervised learning, the situation is typically different because we don't have this output. We only have the input. And our goal is to learn some hidden structure of the data. It's kind of not very good problem statement because we don't say explicitly what we want from our. We just want to have some exploration of the data, of properties, and maybe in most cases, we can say that we want to recover the distribution of the data, so we have some points. And in case of clustering, basically we say that we are trying to have these three different clustering and some density related to each of the cluster, and in like one-dimensional setting, we have some observations here for our feature x, and we want to recover our distribution that we can later use for different purposes. For example, we can say that here we have anomalies, here we have anomalies, and there would be our anomaly detection based on the density, and we compare it to some threshold. If it's smaller than a threshold, then we say, okay, it's an anomaly. And basically, all of unsupervised approaches can be can transfer it, can be reformulated as a problem of the recovery of some probabilistic distribution. And like it's kind of explicit for clustering. For Gaussian mixture models, we have like explicit formulas. For density for Kamins, actually, we also assume that we have these clusters of equal form here, and we have this like Gaussian bells, Gaussian curves centered at each of the centers for Kamins cluster. For another types of models, it's not as explicit, but still kind of similar to what we can see about clustering and about general density estimation. The difference is that typically we try to recover some probabilistic distribution in lower dimensional space. Basically, there is a manifold here related to the data, and then on this manifold, we again trying to recover the density. So again, this is the density, but also we have additional assumptions that this density lies not on all our RD, but rather we have some smaller dimensional part of this RD that corresponds to our dimensions. Basically, we also recover the density with additional constraint. And we can say something like this with AutoEncoders. Relative coverage in more details, but basic idea is quite similar to PCA. PCA, we can also say that, okay, we have some object X, we have some linear transformation to have that here. Yeah. Not a vector, is rather a matrix of coefficients. And we have this lower dimensional representation, and also we can try to recover X from that with, okay, if that of the same dimension, but if it's not the same dimension, we can say different transformations that leads to our estimation of X from that. And basically the model related to the axis given some latent representation in low dimensional space. And basically we think about something like this when we define more complex AutoEncoders. So we have this encoder. For PCA, it would be a linear function. A decoder for PCA, again, it would be some another linear function. And we, for example, try to minimize the difference between X and X recovered from our latent representation. We can define some norm, for example, L2 norm. We want this L2 norm to be minimized during optimization of parameters, such as transformation of the parameters and other parameters. And so basically we improve on what we have for our partial component analysis, but with a more complex function, something like G delta and delta G of X and F delta F Z to get X. We'll cover more details, but the basic idea is the same. We again try to find the manifold, the data reliable. Okay, typically what's the problem with all these approaches is that, okay, if you want some density estimate, typically it's kind of complex to have good estimates, kind of, because of the course of the dimensionality. As we have more and more input dimension, we can imagine it's a basic density estimation approach as some kernel approach, and kernels fail if we have a large enough dimension, because basically we have no or almost no points in a neighborhood of each point, so our density estimation would be poor. And this kind of problem for many approaches related to unsupervised learning, in particular when we think about clustering or direct density estimation. For dimensionality reduction, it also can be the case, but it's kind of easier to deal with because we right now assume that we don't want four-dimensional manifold. Reduced dimension manifold in this case, we kind of have lower dimension, and consequently we have a chance to estimate density accurate in this lower dimension. So basically we have these two paradigms, and we can say that for unsupervised learning the problem is much more complex because we have no explicit goal actually, because find some underlying structure doesn't sound like a good mathematical problem. Instead, we have this kind of equivalent to density estimation problem that we want to solve, and so we will be able to see if we can deal with it. A pair of words, why we need it, why we can't solve all the problems with this supervised paradigm. Maybe the basic motivation is that when you think about some kids, these kids like learn from the world, and typically with little or no supervision. They actually like some age just observe what people around them do and learn by observation without explicit notes and without actual explicit understanding of what's going on. So I hope that we can imitate the process, the natural learning process that we observe for kids, for animals, for any objects. Another issue, like more mathematical, less philosophical, less related to humanitarian, like some humanitarian sciences, is that we don't have much labeled data in the world. If we want some data to be labeled, typically we have to label data itself or delegate it and spend some resources on labeling. It's kind of complex, expensive procedure. Quality is not very good sometimes. So instead, the goal is to drop this expensive step and try to learn from the data itself, from unlabeled data. Or at least we can label only a small part of the data. And so in this case, we will be in the paradigm of supervised learning. But still, many observations and many approaches from unsupervised learning apply in this scenario. So we just don't want to label the data because it's expensive. And on the other side, in many cases, we can observe that, okay, if we want to use all the data from the internet, all texts, for example, and in this case, for NLP, we basically try to train this kind of unsupervised models. In this case, we also emphasize that we typically deal with a bit different problem. We don't learn this hidden structure as some density, but rather we learn this mapping to some embedding space. If it's X, and we have some J of X, some Z, and this Z is an embedding of X. And these are quite useful, and they represent the structure of the data. The most important features of the data we want to compress in this vectors related to X in some way. This is our representation, our embedding. A couple of words to say what it is, but in any case, this is like the most popular and the most powerful approaches in many areas. In NLP, like in image recognition, we still can think about our deep learning models as representation learning tails and some small heads on top. Basically, we can say that in many cases, we just learn this model from X to Z. Like the largest part of the network in terms of the number of parameters and in terms of the number of layers, and small, like even linear model to obtain some classification result, obtain the level. So basically, to run the representations, you can say that we don't need VAE if you have enough data. And instead, we can try to learn this black box alone, and so again learn some representations that can be useful in many problems. And basically, in the end, we can say that this embeddings, these methods to solve unsupervised learning problems, is a way to understand the structure of visual or NLP word or the word in general. Like it's a way to perceive what we need to think about the semantic concepts here. So maybe it's one of the most important problems we can deal with when we think about machine learning, at least from philosophical point of view, and as you all know, also from the point of view related to learning from large data we have on the internet. So we have like kind of important part of unsupervised learning when we think about our models, our data, like some generative model for it. We say that we want to recover the distribution, and the goal of this recovering is the ability to generate even more data for some reason. So we say that we have some training data generated from the data distribution here, like original distribution. Then we train a model to have this distribution like close to this initial model here, or data, sorry. And so if you have the distribution, and as you seen during the course, we can try use the distribution to generate something. So we can generate new data based on the distribution. Again, it's like a central problem in unsupervised learning. We want to recover the density. It's like a very explicit stated here. We want our distribution of the data. So we can use later to generate some data. It's again kind of approach when we think about generative models that have many applications. Like every one of you can imagine some guns for generating of images, or like recovering some part of the data if we don't have this data before. For example, we can drop some part of the image, and if we can still recover it. And we can, for example, in Photoshop, there are a lot of tools that are related to image processing and that are related to kind of using generative models to that states that if you know the distribution of the data, we know everything. So we can use it for our benefit and generate, for example, some strange things like back designs. Okay, maybe it's topic for a separate lecture to think about something like this. Two more examples are time series data. We still think about it that we want to generate a model for data to generate some data. It can be used, for example, to fill the gaps in the data. If we have some missing time series data, we can try to say, okay, curve and something missed in between, and against the curve, and we want to recover it in kind of what, for example, I'm doing for oil and gas data. But more general, we can think about a way to learn representations in NLP to predict like future words in generative models for text like GPT-3. And also we can think about something like this when we are doing a reinforcement learning, which kind of hot topic a couple of years ago, and still we have a lot of papers related to it. And last point as a slide. Again, when we train the generative models, we have some representations, and these presentations are kind of useful to solve many downstream problems. If we don't have a lot of supervised data, a lot of label data for our problem, we can say we start from unsupervised data, learn some generative models. Usually there is some representations in between, and if you have these representations, we can use them to solve some downstream problem by fine-tuning this model or learning some full connected layers on top of it. As for all other problems in machine deep learning, we have a lot of methods related to how we can generate something. You know some of them, at least by names. GANs here, my Boltzmann machine here, something you typically know, and also like general Markov chain idea of data generation model. Also, we can try to have some explicit models for our data, like tractable density. But today we will focus here on variational encoder related to some approximation of the density with an additional assumption that it lies on some lower dimensional manifold. So let's start with very basic autoencoder. So our goal here is to learn in a supervised way some lower dimensional future representation of some unlabeled data we have in our training sample. So we have a sample of x's again, and we want to train an encoder that provides some features for x, some lower dimensional representation for it, like just simple comment. We can think about different approaches to do it, and maybe the simplest model we can have is just linear layer, and we have PCA in this case, for example, and when we minimize L2 norm, and something more complex, typical for deep learning, typical layers like convolutional neural networks. So that's features. And we typically say that Z is more useful, so it's like more informative features. For example, you can have this small model on top of this layer to predict something which is impossible for the initial axis, because when we will have just linear transformations of pixels, we will have some very bad approximation for typical problems of image recognition. So instead, we want some useful features. And also, typically, we want this future representation to be smaller in terms of dimension, like what we have next. So if you have this kind of 2028, 2028 images, something similar to ImageNet, and if one don't want to have to be 40,000 of features, we wanted that something smaller, like 520 and so 12 and so. So we want to learn some meaningful representation, and this representation to be of small dimension. The problem is how can we learn such a representation? And natural approach here is an autoencoding. In this case, we just encode the original data and add additional step, decoder. So we say if we encode data, then we'll be able to decode back if we keep most of the information in this vector set. So after encoder and decoder, we have some x is a hat, and x hat should be similar to what we have initially. And so we have these two parts. For decoder, we also have some kind of deep neural network with the convolutional layer, up convolutional layers, fully connected layers, and so on, like usual stuff, you know. And our basic thing about autoencoder is the loss function for many other models. It's quite simple in its original form. The loss function is the difference between the initial x and this x hat. So we try to reconstruct initial data, we define some architecture, and so we just use the backpropagation to calculate derivatives, and we use gradient descent to train the data. So if we train everything in the correct way, then we can throw away the decoder and have only encoder to have our features, to have our permutations we want. And so basically that's all for this basic autoencoder model. No probabilistic interpretation at the moment, but still some useful features sometimes. So if you have this encoder on its own, then we do some kind of transfer learning for this particular model. In many cases, it's kind of useful not to use the model as it is, but fine-tune it by training not only the classifier on top of features, but also some. Okay. Also, it's kind of interesting that we can try to, if we see some typical values of that, we can try to keep it kind of generative models. But still, we are far away from this goal in this particular model. The first reason is don't have the explicit distribution of PZ here. So because we don't have any probabilistic assumptions here, we can say something like this, and we can adapt, for example, the PCA paradigm to generative models. But to think about it in a more consistent way, we need some additional probabilistic assumptions. Also, the pictures we get from autoencoders are not very good. Typical problems mentioned in the first place is that we have very blurred image here because we try to smooth everything, and if we smooth everything is this autoencoder model, it's not a good model because it does not, as good as reality, it simplifies what we can get in there. So we are in need for more complex model. The first reason is that we still don't have a generative model. And in the first place, because our autoencoder typically is not very good, to be honest. They still need some improvement and some tricks to train each to get more realistic features. So let's switch to the third part of our lecture, to variational autoencoders here. And so we can say that we want to define some probabilistic. Okay. Any questions to the moment? Please write plus if everything is clear and we can go on. And if it's not the case, please say, let's discuss something more details. But generally, I suppose this material.
I mean, how to sample new images from autoencoders, and why it is sufficient to sample from normal distribution?
From normal distribution, okay, we don't have no explicit distribution right now. What we can try to do for autoencoders, we can try to train a separate model to generate to have some distribution of Z. And we can get the Z, for example, from the trained sample of pairs of X and encoder of X's, and we have a sample of Z values. And if we have this distribution, we can sample from the distribution and get it to decoder to have some kind of generation of images. It's, as you can see, like it sounds like something artificial, and so we are in need of more explicit model, more explicit probabilistic way of thinking about this problem, and that we will do later. And also by Gaussian distribution, we don't have Gaussian distribution at the moment, but the answer for this question later, because we will have them. It's like the most natural way to think about anything we have in the dark. Basically, Gaussian distribution, it works very good. It has a good properties. You can calculate practically everything for Gaussian distributions. And also, sometimes we can try to incorporate more complex model. For example, when you think about variational autoencoders, there is some modification of it that use not a single Gaussian distribution, but a mixture of Gaussian distribution. For example, if you have this conditional variational autoencoders and have some labels or some features we want to incorporate in our generative models, we can do it. And in this case, we can try to use a conditional model and or a mixture of Gaussians. But I suppose that mostly people don't assume something else if we have some explicit assumption on the distribution in the space of the representations, in the space of features. That's it. And if we have no other questions, let's go and look at variational after. Okay, thank you, Andrei, for the question. And so we say that typically we want some manifold that represents our data. And we want some generative model to generate images from this manifold. So we have a connection between Z and between X. And as we know that actually we live in a lower dimensional space, the space of all images, we don't need to define the distribution on the low or high dimensional space of X's. That's what we don't need. Instead, we can try to define the distribution only for important features here. So we will be able to generate with this model these images as our goal for generative models generated from latent variables Z. If you write the formula, you can just write conditional distribution for X to get the density of X. And it has two terms. The first term is our prior density in the latent space for that. And also we have this conditional density for X, given that we generate something with a decoder in terminology of autoencoders. That will lead to the distribution on axis. So we can, for example, try to maximize the density to generate something and run this process many times to get many images. Also, we can try to solve other problems. For example, we can restore the part of the object and we can fill this gap with something, I don't know, like this. Yeah, not very good. I'm not a very good generating models of faces, or at least something. We can also try to have this super resolution from a small image. We want to have large image, and in all cases, we can say that we define the distribution, maybe conditional distribution, and we want to find Z that corresponds to this particular X by maximizing this product of logarithm of the density, conditional density of X given Z, and of prior, we as usual take logarithm. So now we have not a product but a sum. We maximize with respect to this density and have this Z hat. This corresponds to X. So now we can say that our X hat is like the most probable X hat is like this, a decoder applied to Z hat. And again, we have this intractability problem. We can look at this likelihood for our axis, and as usual, we can say that for Gaussian, for the prior, we can use Gaussian distribution. Like the most natural choice, simplest choice that typically leads to something good. For a decoder, we can introduce something like this. We say that we have a separate model for a mean value and a separate model for the variance of the distribution, and like a deep narrow network that corresponds to this assumption. And we can say that we have a separate narrow network for mean value, separate narrow network for the variance, and finally we have a Gaussian distribution related to X. But in this case, because this mu and sigma are deep neural networks, we can explicitly calculate this integral because we have this complex distributions. And also, in many cases, we're interested not in X and the related distribution, but rather we are interested in what we have in a lower dimensional manifold. And in this case, we don't have this posterior density as it is, unfortunately. Because as in all Bayesian models, we have a bad part related to how can we model this evidence, in this case, not evidence, but rather a distribution of X's, but still we can't do it like this. Intractable and deal with this. So again, a problem. And as we have a problem, we can try to find a solution to this problem. As in this case, for variational AutoEncoders, we typically say, okay, let's find another approximation as we need this posterior density and we need some distribution of that given X. Let's try to learn another model, an encoder network related to this distribution. We hope that this Q would be a good approximation for our. And again, as we like a lot Gaussian distributions, we say that our encoder also defines some Gaussian distribution. We have some nonlinear transformation of X's to mu and sigma. In this case, not mu X and sigma X, it's rather mu phi and sigma phi. But we have this coordinate. So now we have this whole mechanism to deal with in our variational AutoEncoders. We have some prior assumption on that, and we have some encoder that defines the distribution of that given X, and the decoder that defines the distribution of X given Z here. And basically, we assume that there are from some Gaussian distributions, and we'll be able to recover the images using this variation. So the schema is like this. When we use our designations, we have this manifold of that, and we have two mappings. One mapping that provides the distribution of that given X, another provides a distribution of X given that. Also, we can say that now we can try, as always, write down the marginal log likelihood. The marginal means that we integrate out everything we don't need. This integrate of P of X and Z, P Z with respect to Z to integrate that out, because we don't have like explicit Z, we have a rather distribution in the embedded space related to X. And we can write it in the following form. We have a Kolbe-Kleber divergence between the distribution of that given X and this kind of approximation. And we have another term here. As we know, okay, something we already discussed when we do Kolbe-Kleber divergence here. And as we know that Kolbe-Kleber divergence is greater or equal to 0, then we have a lower bound for our P, this L. This L can be decomposed again in this terms here again. And this variation over bond takes the form of the sum of two terms. The first term is minus Kolbe-Kleber divergence between the prior distribution of Z and Q of Z given X. So we want the distribution to be close to each other, so if you have some mapping from x to z, or to the distribution of z given x. This distribution should be close to our prior assumption. Okay, some Gaussian distribution. And also we have this second term. If we have some distribution of z given x, and then we recover x given z, so we apply encoder, then decoder to recover x. So we can say that something like we have as generation of x, not tilde, but rather x hat from x. We want this generation to be good. So it would be this two guys to be close to each other. This. Basically, it's similar to the likelihood of the data. And the first term is something like regularization. Because we don't want, for example, we can say that in all cases we want variances to be 0. And in this case, we have usual autoencoder. And we know that autoencoders work poorly, and we want something more interesting. So basically, we have regularization here, we have latent representation here, and we have this reconstruction here. And so basically, that's our probabilistic model related to the variational autoencoder. We kind of familiar structure of terms, and we hope that it will work in there. Also, we can say that we have this ELBO variational lower bound for our sample here. So we replace these guys. We don't know because we don't know like explicit distribution of x's with these terms that we have formulas them at the previous formula. So we sum them over all our x's. So now we have a functional to maximize. So maximize it with respect to parameters of encoder and decoder. For encoder, we have this guys, and for decoder we have another terms here. And if we maximize this functional, we maximize the lower bound of the likelihood of the data. So basically, we try to recover again the density. So variational autoencoder is a way to recover the density of the data, given the assumption that actual data live on a lower dimensional manifold. Explicit form, as you can see, for a model has these terms here. And this is also important because it's a reparameterization trick. If we write down everything in the initial form, we will not be able to get the gradients to have the back propagation of from here to here. So rather, we say that we have this, we don't generate that as a result of work of our deep neural network. Rather, we say that we have this random variable as sum of two random variables. It's not a Gaussian random variable. We decompose into the term related to the mean value and to the variance. Basically, we have for that what we assumed before, but we can generate this epsilon in a separate way. So we generate epsilon, and now if you generate epsilon, we can back propagate through all those guys by fixing the epsilon because we generate. So in this case, we are able to do the back propagation by reparameterization trick. Actually, reparameterization is something like not very old, like introduced maybe even in Variational paper, or at least it was the start of the wide usage of this approach, reparameterization trick that allows passing of the gradient through the layer when we have some random variables. In this case, we generate some random variable, and so our full pipeline is not random, deterministic, and we can pass gradients. Sorry, I hope it's clear. And so again, also guys here, here, and some explicit forms for our guys. As you can see, is kind of similar, kind of good, because we have this Gaussian distribution assumption for each of these guys. And again, we have everything we need to define variational after. We have regularization term here related to the variances. And we have again the reconstruction error, and actually it's something like close to x minus x hat. And we have the sample. And so we can, for example, see what's going on when we train the model like this for our variational autoencoder data, and we can apply it for example, MNIST and writing digits. So you know, and each cloud here represents representations related to images of some digit here. And as you can see, we have 10 separate clouds here, well separated, related to each separate digit. It means that if we train this variational autoencoder, we are able to produce high quality representations. And if we for example, will define a classifier on top of these representations, and this classifier is something slightly more complex than any one, then we'll be able to get high quality classification of MNIST digits. Okay. Also, we can say that right now we have a generative model. We have this Z, and we have some prior P of Z, which we believe is close to X, oh, excuse me, of Z given X. So if we sample Z from this guy, then we can get the most probable, for example, of X given Z to generate this new representation. Also, sometimes we can say that these features in our embedding space are tractable. This random variable or these variables of Z are independent in the Latent space. So we assume that we can encode different factors. For example, for two-dimensional representation of MNIST, we have this transfer change of variables here. And we can say that if we vary Z1 or we vary Z2, we smoothly transfer from one digit to another here. And you can find a cluster of zeros, fives, threes, eights, and so on. So we kind of compactly pack our digits into two-dimensional space. Same thing occurs if we look at more complex data sets, and we can try to guess about particular features related to each dimension in the embedded space. As we deal with something smooth, with a smooth embedded space, then we definitely change something and change it smoothly. And in this particular example, we can say that varying the first dimension, we vary the degree of smile on a face, and varying the second dimension, we vary maybe the second most important parts of our representation. We vary the head pose. As we increase that too, we can have a different angle of our head. So they we can try to use this approach to generate some faces. And as you can see, we have some results. They're not very inspiring. Again, we have some smoothness problem. So if you apply it like this, we have not perfect results, but they're much better than what we have with vanilla autoencoders. And some autoencoders can do even better, but still not as good as what we have for generative adversarial networks and for the models related based on, for example, diffusion paradigm that we'll consider later in the course. So basically, we have some generative model of limited power, and actually it was the best we can get is 2012 and some years after it. And also this models is kind of useful in different areas, and we are not thinking about like faces, but maybe about something simpler. For example, for MNIST it works quite good and works significantly good, better than what we have for vanilla autoencoders. And even for CFR, we typically can train variational autoencoders that can generate quite realistic images from the space. What I have not talked about yet in this talk is that as we have this probabilistic interpretation of our generative model, we can try to make it more complex and include explicitly some variables we haven't included in the data. For example, we can use a CVAE. It is a conditional variational autoencoder. In this case, we can generate X, but also given Z. But also given, for example, some class level or some feature. For example, we want a hair to be red in the image, and we say that okay, we have additional variables related to this case. Also, we can try like this joint generative models. If we have some labeling of the data, we can try to shift from unsupervised paradigm to the case when we know something about the class labeling. And so we can incorporate this information about labeling into our generative model. In this case, we generate the digit we want to generate. So we have this more convenient model, more tailored to some specific application. And this is not the limit. There are large family of variation of autoencoders, of variation, even of variation autoencoders related to some problems. And also, I would like to, if you have some time, think about adversarial autoencoders. For example, in this case, we say we redefine the loss function basically by looking in a different way at our regularizer. We don't have this Kullback driver between our prior and our distribution queue, but rather we say that, okay, it's not common for distributions, it's not convenient for the distributions to calculate the Kullback driver divergence. But rather we can try a discriminator that try to distinguish results of the work of encoder and some generated like that from some distribution P. And in this case, we can match our generated with encoder samples from our original distribution by training a discriminator. So by going by one step into the direction of generative adversarial networks, it works better. And for autoencoders, it was like in 2018, I suppose, state of the art for these types of models. And you can look at this paper. It's kind of interesting and produce like a couple of tricks how to deal with this scenario and what kind of distributions we can deal with. But it's like kind of external material to the lecture. And so now it's time for another question, if everything clear. And can we go on with the lecture today? Again, you're expected to answer plus or ask the question in the chat. Okay, thank you. As we have some time, I would like to have some I would like to have some more general intro into generative models. And let me wait for it. Let me wait for 1 minute, please. So we have this supervised paradigm that's not very useful in many cases. So the idea is to try to advance and do some self-supervised approach to deal with it. So we can say that if we have one input and another input, and we believe that they have the same semantic feature, there is a call on the first figure and the call on the second figure, then we want the embeddings or representations is that we have here that and that. Prime would be closer to each other. So this is the basic idea of general self-supervised learning. And basically we have many approaches to it. And we looked at the part related to autoencoders. We can, for example, and we covered this small part, but this is not the only approaches we can apply to deal with generative models, or in more general sense, contrastive models for self-supervised representation learning. So our goal is still to find some distribution for the data, but we say that maybe we can find something better in different areas because autoencoders are not perfect. And for sure, we can say something about GANs, but GANs also have some limited power because actually the embeddings for GANs is kind of like not explicit if you think about this general GANs. when we just generate that from noise and then apply some generator to it. Because we have this like Gaussian distribution, and it's kind of simple and it's kind of looks strange in some problems if you think about more general generative models. So we try to learn these embeddings in a different way, and we focus later in this lecture on the contrastive learning. Also note that there is like kind of combination between generative contrastive learning, generative contrastive, partly related to adversarial training when we try to fool some model and field model to be not fault according to some criteria. So more like the more general problem for generative models is we try to recover something because it will allow us to write down the loss function explicitly. For example, we have this whole image here. So let's drop 1/2 of the image and try to recover this part from the left part here and have some representation in between. And if we have this representation in between, then we have some representation for the whole image. If we go back and look at the whole data sets and apply the same model to the whole data, to the whole object, then we have some representation of the object encoder of X. We can apply different strategies to train something like this. When we're talking about NLP, for example, it's typical to mask some word. For example, there is a sentence, we mask a word future, and we learn an autoencoder to recover this word. And if yes, we have something in the middle, we have this representation here. And that's one approach. Another approach is, for example, replace some words to the, for example, something like this. And for each word, we try to predict what is this word was replaced or not. So we solve this classification problem. So we can explicitly define the loss function. Not probabilistic, yes, but quite powerful. And in this case, we again have quite impressive results. Basically, this idea with replacement is a lecture approach for the training of self-supervised natural language processing models. Basically, we can try also autoencoders, which we discussed in the first part of the lecture. But let's also look to another part of what we can do with. In particular, we want to think about our self-supervised models, and in particular about contrastive learning. Again, we have some image and we have some encoder. And we hope that encoder will produce a representation H from our image X. So we want to train this guy to be good. What is good? Good if the representations are consistent when we look at different images. And as we don't have supervised data in this case, so we are looking with self-supervised data, what we are doing, we say, okay, we have initial image. Let's try to apply some transformations to it to keep semantics the same. For example, we apply in this figures crop of these images. So we have one image XY and another image XJ. And after application of the encoder, when we have the embeddings HI and HJ, we want them to be close to each other. HI minus HJ should be small. But if we have some other image, we crop it, apply encoder, and have HK. We want the guy HI and HK to be different from each other. So we want this distance to be small, this distance to be large. And we don't know what is the scale of these distances. So we try to encode into our loss function the difference between these two guys. So this difference should be as small as possible. So we should minimize the sum of all AJK, of all triplets of images with respect to our parameters of the encoder, because each I or J are the result of application of the deep encoder model to our data with respect to some parameters of the encoder. Basically, we are not talking here about generative models. For sure, we can try to adopt it, but our goal here is to rather find some distribution for 3x, or in other words, construct meaningful embedding space. So after learning, we say, okay, if we have some anchor and positive pair, and anchor in negative related pair, with anchor being this image, and negative pair to be this guy, and positive pair to be this guy. Then after learning, we expect that anchor and positive would be close to each other, and negative pair would be far away from this pair. And this basic loss function works quite good. And this was called triplet loss or something similar to it. Sometimes there is some modifications to this guy. Penalties is not that strict. For example, we can say that we penalize this distances if it's larger than some threshold tau, so maximum tau. And if it's smaller, it's okay to have some freedom, because basically, okay, we understand that embeddings of xi and xj shouldn't be the same. Also, okay, is it clear for now what we are doing? Please write down a plus sign here if it's clear. Okay. So let's try to think about something more sophisticated. And a good example of this approach is an approach that actually does not need the negative samples. Train only on positive pairs. That's the magic that's happening. And what we need for this magic to happen is to say that in the first place, if you have an image, we generate two augmentation of this image, for example, random cropping or distortions, Gaussian. This triplet is enough. We have this encoder again, and have two representations here. Then we have this additional projection head. I think we need this because we need to think about what kind of features about the image we keep and to match this representation. So basically, in the first place, you can say something that you want this guy to be small, but it's like sounds not very good idea, because we can say, okay, we move all h to all f of x is 0 and would be small. But if you have this additional projection head and a contrastive loss on top of it, so basically we say something about that Zj should be small. Then we have this good agreement we have in the end for our model, and if you train it, we have a framework for contrastive learning. During evaluation of this model, we for sure don't need this projection head, but rather we have only this part that provides us with a representation of x. We can try to do even better, and we can use only one latent representation. In this case, we compare not to the similar model, but rather with smooth our model. So we say, okay, we have this our model as this step with parameters theta that is here. So we generate some view, like some augmentation. Then we construct a representation using our model F. Then we project to get Y this designation. Then we project here to get Z, and we want Z to be close to some other representation. And how we produce another representation? We again generate some view, apply some FC, apply some projection, and we get some different embedding. And so we want this prediction to be close to Z of theta to be close to Z psi prime. The question is how we have this, where we get this psi. It's kind of everything, but what we are doing, we say, okay, we have this, okay, what we have is trajectory of loss function, and we have a lot of models here. We have f g minus k, f g minus 2, f g minus 1. So we say, let's have this xi to be a mean value with respect to some time window. So from I from 1 to k, g minus k. So we average the model. We have previous steps. And for this smoothed model, we want nu f theta to be close to, in terms of generated predictions here. We can say this is kind of similar to what we have, for example, for the model distillation, when we merge two models and we have this larger, maybe more powerful or smoother model. Yes, it's true in a way, but in the end, we don't need negative pairs here. Okay, basically it's more complex formula, but instead of just mean value, but it does not. We shouldn't bother us right now, I think. So now we don't have negative pairs, and I want to cover a bit on how we assess the quality of self-supervised models. So like if you want to test the representations here, we can try to train a linear classifier on top. So we train logistic regression if we have like some imaginary training model and we want to solve the classification problem and see what's the accuracy of the imaginary model trained using this like boost your own latent approach and some supervised approaches that train explicitly on the labels. As we see, for the basic method, we have some gap in between supervised method and Bayesian, and this gap is about 2% here. For the model that has like 25 million parameters. So basically we have this gap, but we are quite close. The gap is much smaller if we increase the number of parameters in the model. As you can see, the gap is quite negligible between Bayesian and supervised model. As you can see, we have other models here. Okay, this guy I described to you at 2 slides ago, CLR is below Bayesian, but Bayesian almost matches the performance of supervised model. Another approach, okay, yeah. For evaluation, we can try to not use top 5, but rather top 5. And basically, we can see that we get quite good models and quite close to the supervised counterparts if we evaluate in this way. Also, if you have good representation, it's quite common to think that it would be good for transfer learning. So we train our models on ImageNet, then try to transfer it to other data sets. We can use linear evaluation approach when we train a linear model on top of our representations. Also, we can try to fine-tune the model. as you can see, if we fine tune, we typically have better models here. But if we consider linear evaluation, so we use the representation itself, we say that BIOL is kind of similar or better than supervised approach, and also to another supervised approach that was sought at this moment, SimCLR. We also can try to transfer the results in a different ways. For example, we can try to use these embeddings to solve the semantic segmentation problem and object detection, this or depth estimation. Like for all these problems, we can see that this approach based on boosting your latent is the top, and it's even better than supervised embeddings, because supervised embeddings we are training to solve a different problem. What's bad about this approach? Why it's not like universally acknowledged and used in many cases? The problem is still need large batch sizes. So the default way to train the model is to use this batch size of 4096. It's quite a lot. It requires a lot of memory to train, and the models themselves are very bad in terms of they're very large. And if we drop the batch size for BIOL, we have this decrease in performance. It's not as dramatic as for SimCLR, but still, if for small batches, it's kind of very hard to get state-of-the-art results. We have this 3% drop. Maybe it's not that bad actually, because okay, it was 63, I suppose, some 70. I think it's okay for top one ImageNet, especially if you consider like pre-deployment approaches. But okay, it's lower than SOTA. Also, it's important to say that if we drop some augmentations, then we drop the quality of the model. And in this case, the drop is quite significant. If we use only crops, we have like minus 13% of the accuracy. And the same is for different types of augmentation. If you observe some drops, it's again not as significant as it was for SimCLR. So this method is more robust for some reason, why? But we have it like this. So if you want to train self-supervised representation, we can do like this. And also there are other approaches that is more related to contrastive learning. And if you look at the results, they're typically better and so on. Like usual tables, you see the papers that try to promote their own approach, and another one is really great. Again, some improvement. But I have a couple of minutes to finish, and I want to say something about why it works. Actually, there is a paper, quite recent, on why we can work without negative pairs. And we can say that we can prove a theorem that for a simple network, like I suppose, they use one or two layers fully connected neural network. The dynamic of training makes the learned representations that contains the representations related to the features we want to learn. And actually, we don't learn part of the features related to the augmentations. We just, in a way, project image to the space of the semantics we want to uncover, to the actual features we want to extract from the image. If we do everything right, if we apply all the approaches below. This theoretical analysis, say, quite general things. but at least it's kind of an answer to the question why it should work. It's kind of not clear because we deal with the case and we don't have negative pairs and kind of magic. Also, I would like to say that this another problem is discussion of what kind of embeddings we work with, and how can we say that one embedding is better than another. And what we try to do, we try to compare embeddings and local optima related to self-supervised and self-supervised learning. And unfortunately, we find that self-supervised are not as good as supervised. At base, the optima are narrow. So if we go in the, okay, if we we have this initial vector of parameters for self-supervised learning and another one for supervised learning, we fine-tune it to solve some problem, or like fine-tune imagine it. Have two optima after optimization here, well, a second, and we see what the value of the gradient if we try to go out and try to move as fast away as possible from this local optima, and we move faster if we use self-supervised learning, and it's worse in this case because it means that this corresponding optima is narrower than the optima related to supervised learning. Is kind of something like this. So it's more stable, and we get a better optima in this sense. And we can look at these figures from different points of view. Again, we make some stochastic steps in the neighborhood of our local optima, and we can see that loss values is lower for supervised local optima and higher for self-supervised. It means that this optima again is more narrow for some reason. And the same thing happens if you think how long we should travel to get optima for transfer optimization. And for supervised approach, we should travel less and typically get something smaller. Again, the relative distance is smaller for supervised approaches. For right now, we don't understand why self-supervised optimums are better. Maybe we can try to do it later for different problems. And I think it's the end for today. As I have said, this self-supervised approach is starting from variational Untitled and ending up with methods based on contrastive learning. I work quite good. They allow efficient training and they allow transfer learning. And these representations are do meaningful, but sometimes we still like kind of magic happening. Why we should use this and should not use this, especially if we're talking about SOTA approaches based on contrastive learning. For example, augmentation selection are crucial if we want our model to be successful and to be trainable at all. Also, we note that it takes a lot of time to learn such model because you know direct supervision may be similar to what we observe in the real world. If you have supervision, quite easy, much easier to train something. If you have no supervision and you want to develop our own concept on the board, it takes for like a child a couple of years to understand what's going on outside, and what kind of things he can observe and he can do with the tools he or she has. So there is, I think, a road to go in this direction, and I hope that gradually we will be able to provide some Bayesian and probabilistic approaches to deal with self-supervised learning and to make it more understandable in terms of learning dynamics and overall, and faster in terms of how much memory and how much time do we need to train such a model. That's all for today. Thank you a lot and have a nice remaining of the day.
Thank you.
Bye-bye.
Bye.